So I want to start today with one more log rule, and that's this. Log base b of a to the x. If you take log base b of a number to another number, this is x times log base b of a. You can just take that x, which was in the exponent, and move it in front of the whole thing. So log base b of a to the x is x log a. Very useful. So the b and the a stay in the same place. The x goes from the exponent out in front of the log. Okay, now I want to talk about the concept that logarithm is the inverse of exponentiation. Now, let's take a look at some really simple equations first that have nothing at all to do with exponentiation or logarithm. Let's say I have the equation x plus 3 equals 5, and I want to solve for x. Now, I know you can do this in your head, but I want to do this sort of longhand, and we know what we do. We subtract 3 from both sides, and you end up with x equals 5 minus 3, which is 2. So when you have an equation which is assembled via addition, to dig out the variable, what you have to do is subtract. Subtraction minus 3 is the inverse of plus 3. So when you have something that's assembled via addition, to undo that, you subtract. Let's say we have something like this. Two x equals 6. Since we have multiplication here, you know how to get x by itself. You use the inverse of multiplication. The inverse of multiplication by 2 is division by 2. And so you end up with x equals 3. Now the important point is not the answer, which I know you can easily find in both these cases. The important point is the concept that when you have x surrounded by an operation, in this case plus 3, in this case times 2, to get x by itself, what you have to do is the reverse operation, the inverse operation. And we're going to use this to help us solve equations with exponentiation in them. So let's take a look at an example. Let's do an actual word problem. So say the volume of a culture of bacteria in milliliters. So let me give a variable here, volume V of a culture of bacteria in milliliters. T days, so T is time measured in days after the culture is started. Is given by the formula V equals 4 times 1.2 to the t, an exponential function. Right now, already with your experience with exponential growth and exponential functions, you should be looking at this and go, oh, okay, I can see at t equals 0 when the culture started, the volume is 4 milliliters. Right off the bat, you can look at this. And 1.2, I see that's bigger than 1. The volume is growing over time. This is exponential growth, and we could call that 1.2 the exponential growth rate, if you like. Now, there are a few problems we could easily do without using logarithm. So say, find the volume of the culture after 1 day. There's really nothing to this problem. As you know, you just plug in t equals 1. And so you have the volume of the culture is going to be 4 times 1.2 to the 1. That's 4 times 1.2. We really don't even need a calculator for this one. And if you plug in, if you multiply 4 times 1.2, you get 4.8. And of course, that's going to be in milliliters. There are units in the question. We'll make sure there are units in our answer. So for B, let's say I said find the volume of the culture after 10 days. You just set t equals 10. I think we'll need a calculator this time. So the volume of the culture will be 4 times 1.2 to the 10th. Unless you're very good at raising things to the 10th power, I think this might be an excellent time to use a calculator, but you get approximately 24.8, if I'm not mistaken. And again, that's in milliliters. Let me take a look at a different kind of question. I hope you'll remember the point of all this. Say I asked you, according to your formula, when will the volume of the culture be 1,000 milliliters? 1 liter, 1,000 milliliters. Question mark. Well, the initial part of this is perfectly obvious. We set V equals 1,000. So 1,000 equals 4 times 1.2 to the t. And I think our next step's obvious too. We're trying to get t by itself. We're trying to solve for t. So the first thing we do is divide both sides by 4. I don't know if that's obvious, but it certainly is clear. And so what we end up on the right-hand side is 1.2 to the t, and what we end up on the left side, 1,000 over 4, is 250. I'm just going to turn this around. So 1.2 to the t equals 250. I haven't changed anything at all. Now the question is, how do we figure out what t is? I suppose you have two options here. You could just use trial and error. You could take out your calculator and take 1.2 to the this and 1.2 to the that, and you'd figure out whether t was too big or too small. And if you wanted, say, 2 places after the decimal, well, eventually you could zero in on it. But that seems incredibly inefficient. How do we use algebra to be able to solve this equation? Now, I want to come back to that idea that we talked about earlier, that when we have a variable that's hooked together with multiplication and you want to get the variable by itself, you divide the inverse. When you have a variable which is hooked together via addition, you use the inverse, which is subtraction, to get the variable by itself. Here we have a variable embedded in the exponent. It's in the exponent, and we want to get it out of there. So we are going to do the reverse of exponentiation, which is logarithm. We are going to take the log of both sides to any base you want. I'm going to use base 10. You can use base e. You can use any base you want, but I'm just going to use base 10. So log of 1.2 to the t equals log of 250. All I've done is, and remember, if I don't write a number down there, that's log base 10. All I've done is taken the log of both sides. You know, you can always do the same thing to both sides of an equation. All I did is take the log of both sides. Now, I want you to look back at this rule. You see how we can take this variable and pull it out front? That's exactly what we're going to do. We're going to take this t and move it out front. So t times log base 10 of 1.2 equals log base 10 of 250. Now we know how to solve this. We will just divide both sides of this equation by log 1.2. right. And let me continue over here. Get rid of that. So we have the log 1.2 here cancels with the log 1.2 here, so I just have the t on the left-hand side, and I have log of 250, log base 10 of 250, divided by log base 10 of 1.2. And if you type that all into your calculator, the top log base 10 of 250 is about 2.398. And log base 10 of 1.2 is about 0.0792. And if you could have all done this in one step on your calculator, this works out to about 30.28. And that's in days. We want to make sure to put units in our answer if there are units in the question. So, the moral of the story is, whenever you need to solve an equation like this, where you have something to your variable equals another number, just take log of both sides to whatever base you want. I pick base 10. You can do whatever you want. You will get exactly the same answer at the end. And then once you have an equation like this, it's simple. You just divide by log of whatever's over here on both sides to get something that looks like this. Type it into your calculator and you're off to the races.